Hi everyone, welcome to the Living Lab lecture series. My name is Thais, and in this talk I'm going to tell you how I have been using natural language processing to map the global impacts of natural hazards. In the natural hazards field, impact assessment is relevant because we need to identify hotspot areas affected by hazards such as droughts, floods and heat waves to inform decision making to reduce the risk of these areas. We also need this information to evaluate the effectiveness of adaptation measures, to enable impact-based forecasting, and also to validate risk models. However, most of the global databases available have several gaps. First of all, they have a lot of missing data. This figure shows how much missing information there is for every impact category in the most widely used global database, called MDAT. You can see that the number of thefts is pretty well covered, however, other impact categories have up to 96% missing data. A second gap is that spatial descriptions can vary a lot. You can find very generic descriptions of hazard locations in these databases, such as nationwide droughts or floods that happened in the Alps. So you don't really have specific information on the location of the hazards. Third, some hazards are underreported. In this figure, you can see the impacts of heat waves recorded in MDAT. There is a strong global north bias, and also you get the idea that heat waves have only high impacts in Europe, in India, in Japan, when we know from literature that's not quite true. Fourth, events are not often updated. So for slow onset hazards such as droughts, you don't have the full picture of their impacts. And finally, these databases bring mainly quantitative impact metrics, so they have information on the number of deaths or number of affected people, but not so much information on other impact classes. However, scientific literature shows us that impacts go beyond human and economic losses. Hazards can also affect people's mental health. They can have effects on food supply, infrastructure, but we don't have structured information on that. Mostly information is spread across scientific papers or reports, and we need to find a way to structure this information. And this is what I'm trying to do. By combining natural language processing and machine learning, I intend to extract systematic information on the impacts of natural hazards from scientific papers. And to do that, I'm combining two main steps. The first one is to detect relevant papers from literature, and the second is to extract and classify the impacts reported in these papers. So the first step in this methodology is to collect potential relevant papers. And to do that, I created a query that combines terms associated with different hazard classes and terms associated with different potential impacts of these hazards. I use this query to search for papers in two scientific databases, which are PubMed and ScienceDirect. These are the query search terms that I use to search for papers associated with storms and health and well-being. The idea is to collect as many papers as possible that can possibly be related to the description of the impacts of different hazards. With this query search, I got over 13,000 papers from PubMed and over 47,000 papers from ScienceDirect. But of course, not all papers resulting from the query search are specifically describing the impacts of natural hazard events. So to select the actually relevant papers, we built a classification model. Initially, we selected a random sample of the papers and we manually labeled them based on title and abstract. Then, we fine-tuned SciBird to classify the remaining papers. SciBird is a transformer-based language model which was pre-trained in over 1 million scientific papers, which gives it a good understanding of scientific language and terminology. We trained the model with an active learning approach, and this model indicated the presence of 2,300 relevant papers in our database with 94% accuracy. Once we identified all the relevant papers, we extracted information for each of them. So using the ScienceDirect and PubMed APIs, we identified journal title, paper title, abstract, full text, publication year, DOI, PMID, and the source. That means if the paper was extracted from the ScienceDirect or from PubMed. Important is to mention that we are only using open access papers licensed under CC BY. That means that this allows us to use their full text for information extraction. The next step was to identify and to describe every hazard event investigated in the papers. And to do that, we use large language models. Large language models are not only good in summarizing information, but they can also be helpful to extract specific information from text if we do a little bit of prompt engineering. In our case, we wanted to have information on the date, location, and hazard class for each hazard event described in the text. So, one option is to give a list of hazard classes for the model to choose one that corresponds to the hazard described in the text. It's also useful to give the model an example of how you want the answer to look like. So that's what we did here. We give the model an example of the JSON structure that we want the model to follow. That makes it easier to post-process the response we get from the model. So we can do a JSON parsing with the answer we get, and then we post-process the information we got from the large language model. So as I mentioned, for every paper we identify the hazard events described in title and abstract, and for that we describe the hazard class, the location, that means we identify the country, the region, the city where the hazard happened, and the start date and end date. We also do a sanity check to see if the answers we get from the large language model make sense, so we detect all dates mentioned in the text and we try to match with the answer we got from the LLM, and we try to see if there is any mismatch. So after performing all these steps, this is the hazard distribution that we got for the papers we are analyzing. You can see a small global north bias, and this is because we are only analyzing English literature. In the future, we also want to include papers published in other languages such as Portuguese and Spanish. Then, after extracting the information on the hazard events, we went to the full text to get information on the impacts of these hazard events. To detect impacts, we first perform a classification step where we tokenize the text for each paper into sentences. This means we break the text into sentences, and we then classify the sentences in each paper into 17 different classes. One of the classes is named impacts. To do this classification model, we labeled a sample of 38 papers at the sentence level. Here you can see the results of the sentence annotation. We labeled 6,500 sentences, and most of the sentences are reporting results, but we have quite a good number of sentences reporting impacts of natural hazards. Then we classify each sentence in the papers in our database into one of these classes. But so far we are only interested in the sentences reporting impacts. Again, we use a Cybert, we fine-tune a Cybert model, and we got 44,000 sentences reporting impacts with an accuracy of 92%. Finally, once we identify all sentences reporting impacts for each paper, we use again a large language model to classify these impacts and to extract specific quantitative information from them. Here you can see all the impact classes we are targeting at. These include impacts to society, health, water availability, infrastructure, agriculture, and economy. For every impact class, we are extracting qualitative and quantitative information on their impacts. For the quantitative informations, we have specific measures for every class, and we also have specific prompts to get that information for every class. To validate the information extracted with the large language models, we again labeled a sample of 100 papers describing different hazard events, and we calculate for the qualitative measures the cosine similarity between the qualitative descriptions extracted with the large language models and our annotations, and the accuracy between the quantitative metrics extracted with the large language model and our annotations. Here are some preliminary results from our analysis. This map represents the normalized count of reported impacts associated with water availability, and despite the global north bias, we still see a higher reporting of water availability impacts associated with hazards in South America and South of Africa. And here the normalized count of health impacts associated with hazards, and again, despite the global north bias, we see a higher reporting of health impacts in Africa. And finally, for the economic impacts, we see a kind of different picture. Economic impacts associated with hazards seem to be more evenly distributed across countries. And this is the expected outcome of this research. We are aiming at a relational database describing all the hazard events we find in the scientific literature we are analyzing. It can be that one paper has the description of more than one hazard event. So in our database, we will have a description of every hazard event, and this includes the hazard type, location in which the hazard happened, and the date. The location includes a description of the country, region, state, and city in which the hazard happened. It can be that one or more of this information is missing, and the only required field is the country in which the hazard happened. For the date, we have the start and end date. Here, the only required field is the year. And the hazard classes are predefined, and we are aiming at filling one of these classes. So for every hazard event, we have different impact classes. These include health, economic, infrastructure, agriculture, water, and social impacts. Except for social impacts, we have qualitative and quantitative descriptions of the impacts. And for the quantitative descriptions, we have different measures for every class. And for both qualitative and quantitative descriptions of the impacts, we have where we found that information in the text and the reference. This means the paper where we got the information from, and the reference includes the description of the paper title, the journal title, the publication year, and all the information we got in the beginning for every paper. Also, it's important to mention that for quantitative information, we have always the minimum and the maximum value that we find in the text. It can be that we have the same hazard event described in different papers, so we can find different values for the metrics we are looking for. So we always have the information on the minimum value we found and the maximum value. So we have this range. We are also targeting at the commonly measured impact metrics that we find in global databases. This means the number of human deaths, animal deaths, number of displaced people, homeless people, and affected people. Again, for every of these, each of these information, we have the annotation, or this means where we found this information in the text, the reference, the minimum and maximum value, and the location. This is a plus that we have. You cannot find this kind of information in other global databases. We also try to standardize the information we get from predefined nomenclatures or typologies. For example, for agricultural impacts, we have the crop ID according to FAO. For health impacts, we have the diseases codes from the World Health Organization. This makes it easier to work with the data afterwards. With this research, we expect to make it easier to evaluate the differential impacts of natural hazards, and also to enable impact-based forecasting and to detect the areas, the hotspot areas affected by natural hazards. If you are interested in this research, please get in touch. This is my email, and thank you for your time and thank you for watching me.